Hi, welcome back to es346 Basic Thermodynamics. This is module 6.2 on heat engines. The section in the textbook is section 6.3. Here are the two learning outcomes for this module. At the end, you'll be able to describe a thermodynamic heat engine, and you'll be able to quantify the efficiency of a heat engine. So, what is a heat engine? And I think it's a good way to start off with just asking yourself the question, what is a vehicle? So take a minute and think about how would you describe what is a vehicle? Well, here's the definition that I came up with. I said a vehicle is a device that is capable of transporting one or more persons. You may or may not have come up with a similar type of definition, but probably what you did in that process was you said vehicle. What characteristics does it have in order to be a vehicle? Because you probably came up with several examples of vehicles. For example, a car is a common example, maybe a bus or a motorcycle. And those are all examples of what we would call a vehicle, maybe even a bicycle, so it doesn't even necessarily need an engine. And so then you said, well, what common characteristics do these have? And if it meets those common characteristics, then I'm going to go ahead and call it a vehicle. Well, that's the same idea that we're going to use when we want to ask what is a heat engine. So I'm going to go ahead and give you four characteristics that characterize what is a heat engine. The first one is this device will receive heat from a high temperature source. It will convert some of the heat that it receives into usable work. It is then going to reject the remaining heat to a low temperature sink. And the fourth characteristic is that it's going to operate on a cycle. Now, if you have a device that meets all four of these characteristics, we would call that a heat engine. Okay? Now, it's a very general term, kind of like the vehicle. Examples of heat engines are a lot of real engines, and so those are all examples of one type of heat engine, but a lot of things can be a heat engine. So let's go ahead and look at a classic heat engine, and it's actually an entire power plant. And so here on this picture, we show four primary components of a power plant. That power plant has a boiler. Usually the working fluid in here is water. That boiler accepts energy from a high temperature source, usually burning coal, for example. That water gets hot, boils, turns into steam. Then we run it through a turbine. This turbine is connected to a generator, so it can go ahead and deliver some work. And then the pressure drops as we move through the turbine. We saw that in Chapter 5. And then it would move through into a heat exchanger or a condenser, turning from a vapor into a liquid. So it's going to be rejecting some heat to a lower temperature reservoir, something that's some low temperature TL. And then we need to get it back up to a high pressure again, so we would go ahead and run it through a pump. So it's going to go ahead and require some work. So if we look at this, if we look at the system boundary that I have a system that is accepting energy from a high temperature source, TH. In the previous module, we discussed how burners are effectively constant temperature heat sources. It is generating work, and so some of that energy is coming from the energy coming from this high temperature source. It rejects the remaining amount to this low temperature sink, and it's operating on a cycle, meaning that it's just continually going along. There's no buildup of energy inside the system, and the system is also not slowly losing energy. So there's a classic heat engine. It's not really an engine, it's an entire power plant, just like across the street from the university. Here's another device, though. This is called a thermoelectric generator, or it's often called a TEG, T-E-G. And what this is this one that I show. It's only a couple inches on the side. It's a very thin metal plate, and it has two wires coming out of it. And if we look a little closer at what is inside this, and this is a cross-section of this TEG, what you'll see is that these are the two metal plates. One of these is the top plate you see here in the picture. And then in between it are little pieces of semiconductor. And each of these semiconductor pairs, the red and the yellow, form a junction, just like a thermocouple junction. And when that is at a particular temperature, it can generate a voltage. And that voltage depends on the temperature. And so then there's another junction down here. And if that is at a different temperature, it's going to have a different voltage. So if this is a high voltage, I call it V+. This is a lower voltage, V-. I'm going to drive a current in that direction. And if I go ahead and combine all of these in series this way, I actually can go ahead and drive a current through the circuit. And then I'm going to go ahead and have a load down here so I can go ahead and power something with it. So that's the way a thermoelectric generator works. And it's a good question to ask. Is a thermoelectric generator a heat engine? It doesn't really look like an engine in the classic sense. Well, let's go through our 4 characteristics to define a heat engine. The first is that it has to receive heat from a high temperature source. And as I mentioned, one side, the hot side, is going to receive some energy. So yes, check. It satisfies the first one. Here's the second one. It converts some of this heat to work. Well, this work that's being generated has to come from somewhere, and it's coming clearly from the energy I'm adding to the system. This peg isn't building up in energy or decreasing in energy. It's just sort of sitting there with time. So check. It satisfies characteristic 2. Here's the third one. It rejects the remaining heat to a low temperature sink. This also requires something that's at a lower temperature, which is where the heat is released. And at steady state, whatever QH that comes in that isn't turned into work has to be rejected. So it is rejecting some remaining energy to a low temperature. So yep, it satisfies characteristic 3. The fourth one is that it operates on a cycle. And what it means by that is that, as I said, this thing is not building up energy in time and not decreasing. Or we can kind of say that delta U of my system is 0 with time. It's a steady state system. And it is operating on a cycle. So check. So a thermoelectric generator is a type of heat engine. Well, here's where thermoelectric generators actually are being tested right now. And this is the underside of a BMW vehicle. And it's attached to the exhaust manifold. And these are series of TEG units right down underneath here. And what they're doing is supplying auxiliary power to the car. So it's taking what would normally be considered waste heat, which is the heat coming off of your engine out the exhaust pipe, and turning them into some additional electric work. TEGs are sort of cutting edge technology. They're not real commercially viable yet, but there's a lot of research going on with them. All right, so let's go ahead and determine what is the efficiency of a heat engine. And so what I'm going to do, I'm going to use this kind of diagram where I have a high temperature source. I'm going to call that TH up here, and a low temperature sink. I'm going to call that TL. And this heat engine is going to operate in between those two. So it's going to accept some energy up here. I'll call that QH, the energy coming from the high temperature source. It's going to reject some energy to the low temperature sink. I'll call that QL. And it's going to go ahead and generate some work. So inside this thing, this is the heat engine. This is kind of on my power plant idea. There's my turbine, I have my boiler, I have my pump, and then I have a condenser. And all inside there, this whole thing right over here is the heat engine. And so I'm looking at it from a much more macroscopic view, and I'm just putting it all inside there. So let's go ahead and determine what's the efficiency of this heat engine. If you think back to a few modules ago, I said a good definition of the efficiency is desired over required. And so what is the desired product of the heat engine? Well, think about the power plant. What we want is we want the electric work that it generates. We want W. And what we have to supply it is this energy from the high temperature source, or QH. And so my efficiency is W over QH. Now let's do an energy balance over my heat engine. And so at steady state, we know that the energy that goes in is the energy that goes out. So we're applying the first law here. And if I look at the arrows going in, I have QH goes in, and the only arrows coming out are W and QL. So there's my energy balance for my heat engine. And if I rearrange this to solve for the work, I'm just going to move QL to the other side. Work is equal to QH minus QL. Now I'm going to go ahead and put this into my efficiency equation. And so my efficiency now is going to become QH minus QL all over QH. Or I could go ahead and rearrange this and just make this 1 minus QL over QH. And so there's the definition of efficiency for a heat engine. So I'm going to put a little HE down there. In terms of just the heat loads, QH and QL, or I can also write it in terms of the work that it's generating. Okay, let's go ahead and do a numeric example. I have a heat engine, and it's delivering 200 kilowatts of power, and I'm told it's 30% efficient. I want to know how much heat is rejected. I'm going to go ahead and draw up my diagram of a heat engine that's delivering 200 kilowatts of power. It's accepting energy QH, and it is rejecting some energy, QL. And so what I'm trying to find is, what is QL? How much heat is rejected? I know it's 30% efficient. If I go back to my efficiency equation, I can write it in the form of W over QH. And so I know my W is 200 kilowatts, and I know my efficiency is 30%, or 0.3. So from there, I can go ahead and solve for what QH is. And QH is going to be W over 0.3. And that right there is equal to 667 kilowatts. So QH up here is 667. And still trying to find QL. So now I'm going to use my first law energy balance that says the energy in is the energy out of my heat engine. The energy that goes in is QH. The energy that goes out is W plus QL. And now I can plug in the two numbers that I know. I know QH is 667. I know the work is 200 plus QL. And I can go ahead and solve that for QL. And I find that QL is equal to 467 kilowatts. So this heat engine takes 667 kilowatts. It converts 200 into usable work, and then it has to reject this remaining 467 to a low temperature C. A common question is there some way that we can reuse QLow? Do we actually have to end up getting rid of that temperature that's at a low temperature? I often write this as just use of L, use of low. Well, let's go ahead and go through a thought process here of a heat engine, and this will be kind of a simple one to try to get our concepts down. So what I'm going to do is I'm going to add some energy here, QH, and I'm going to go ahead and get some work by expanding this gas, by adding heat, constant pressure, and it's going to go ahead and move this load upwards and going to go ahead and increase its potential energy, which is the work that it's generating. So now I've got my load, it's up here. I'm going to go ahead and remove that brick off of it, and then I'm going to go ahead and I want this to operate on a cycle as a heat engine. So now what I need to do is I need to pull some energy out of this to go ahead and get it back down to its final state. So, and then I could go ahead and add energy again. And this would be satisfying the ideas of a heat engine, accepting heat, doing some work, and rejecting heat and operating on a cycle. However, let's go ahead and look at what the temperatures of my reservoir here need to be. So in this example, we're seeing the gas starts off at 30 degrees. And so that means the temperature down here needs to be like 30.01 or greater. Clearly, and in fact, if it heats up to 90, it's going to have to be at least 90.01 or greater. Now, in order to get it back down to 30 degrees, I'm going to have to be rejecting this to something that's out like 29.99 or colder. Clearly, 29.99, 30.01, I can't use the same reservoir. They can get pretty close, but they never can be the same one. So therefore, my low temperature sink QL always has to be different than my high temperature source QH.